Corona. Okay. Just it was some noise outside, and I got it. And then I'll discuss this blind analysis, you know, that it was a blind analysis for this isobar, and discuss the results. And so the physics which is we are looking for is formulated. I try to formulate it very short over here. It's just a QCD vacuum structure and also the structure or how the hadrons are built. And so it's related in more detail to two questions and chiral symmetry breaking and also possibility or absence of parity and CPU violation and strong interactions. That's all is what about. It also has implications, say, if you would find this chiral magnetic effect, that's what I will talk about, then besides that measuring some of the parameters of this, for example, chiral symmetry breaking, it will also be analogous to baryon number violations in similar processes in early universe, and so it will it would help us to understand how this baryon asymmetry is happening and how it's related to the structure. So this is a picture of energy of the gluonic field as a function of some, which is something like a generalized coordinate, and one variable which is called Chern-Simons number here. And it appears that it is periodic in this direction. And so the minima would correspond to the vacuum, but when there's a minimum for the energy. On the other hand, you see that there are several of them, or many of them, infinite number of them, which differ by topology. And so there are some transitions between those vacuum, and it's called either instanton, which is like a tunneling, or spheron, which happens at a little bit higher energies. And those processes are responsible, it's again some old slide, are responsible for this chiral symmetry breaking. If you want, you can go just read more in really very good and several reviews by those authors like Dmitry Diakonov and Shuryak with co-authors. In fact, this particular picture of energy of the gluonic field I took at some point from this review, and I added all this kind of an axis and instanton spheron. That was for one of my talk. But those processes lead to gluon condensate. They go to the quark condensate. They really responsible for the constituent quark mass with some processes, many others. So that's for chiral symmetry violations. And it also really related to the CP problem. Then there were some papers earlier, but it really kind of started in heavy iron with the paper, with those papers by Harzeyev and co-authors, who basically put a problem that we have just to identify those processes, because without really seeing them, we cannot say that they exist, and they, all those parameters existed before, they're just phenomenological parameters. So we could just do a measurement. And immediately it was recognized that it is a physics which has to be started at RHIC. And this is just from a concluding talk at RHIC Winter Workshop happening just before opening of the RHIC. And already here, Bill Zeitz just put it along with such as ultra-peripheral collisions and spin physics, which is sees the importance. On the other hand, at this time, and so just the early discussion before 2004, it was almost like a random walk. People tried to find some observable which would be sensitive to those processes. Nevertheless, at those years, I would estimate that there are up to 20 people who are actively thinking about that. At least there was intensive discussion in a group at Brookhaven, which is just visited T.D. Lee, or he was a director of RHIC and BNL at that time, and also Jack Sandweiss at Yale. So the group interacted, and I interacted also with those groups. Jack Sandweiss, if people don't know him, T.D. Lee, probably everybody knows. Jack Sandweiss was a very prominent professor, and besides other things, he was for more than 25 years a chief editor of physical review letters. Anyway, so it's in 2004, it's kind of something happened. But before that, as I said, it was more or less people just tried to find some observable. One of the observable I tried just to show over here, what is shown that your reaction plane reconstructed from positive particle and negative particles are different. That means it's symmetric collisions parity violation, and you can look for it. But in 2004, what really happened in 2004 that Dmitry Khardiev realized that all those processes emerge in the, if you put them in the strong magnetic field, and you can calculate it, it's really the strongest magnetic field in the lab we can create. There are another effect which can be used to study what is underneath. And it was just proposed, and I will just talk what it is, this chiral magnetic effect. But because it's kind of quite simple, you will see it almost immediately. I proposed some particular observable, I mean, all ideas are over here, but some practical observable which can be used, and also discuss what kind of a background it could lead to. And this is the chiral magnetic effect. Also, the name came later, not in probably 2007 or even later, probably 8. And what it is just, so if you have a strong magnetic field, this magnetic field aligns the spins which are shown in red. So for positive particle with a magnetic moment, positive is up, for negative it's down. But if nothing else, and you have an equal number of left and right-handed quarks, there is nothing particular happening. You have quarks going up and quarks going down. But if those quarks interact with, for example, instantons, and they change their chirality such that you would be chiral imbalance here, and what shown here, it's only right-handed quarks, both U and D, instead of symmetry between left and right. Spins are still aligned, but because all quarks are right-handed, and you can check the momentum, for positive particle would go up and negative would go down. And so you have this imbalance, and you can look for that. That's why it's called local parity violations. It's happening only in some domain, and the physical consequences of this is clear. The picture became very similar to how the parity and weak interactions was discovered. And so you have your predominant emission of electron along the spin of the, or opposite to the spin of the nucleus. And that was those people, Young and T.D. Lee, this is the T.D. Lee, got a Nobel Prize. By the way, T.D. Lee at that time was just 30 years old, 30, one of the youngest, probably second youngest who got a Nobel Prize. And so, and in the experiment, we want just to measure it. Before going to measurement in heavy ion, I just mentioned that there are many confirmations of this effect. This is just one of the first, probably the first, on the lattice QCDs where people calculated, put in the magnetic field, did see this charge separation, which was discussed on the previous slides. This is a more recent lattice calculations, which also quite relevant for us to have in mind. And what is shown in here, it just shown that this chiral magnetic effect of chiral conductivity appears at the same time when chiral symmetry is restored. And so when chiral symmetry become broken, the chiral current dies out. So which is interesting and important relations and can be used really also to study chiral symmetry relations. It also, this is another directions which stem from the heavy ion and the same things. So this chiral magnetic effect was observed already in condensed matter. And this is just the first paper, and Dmitry Kharzeev here with his colleagues from Brookhaven and Stony Brook, and there are other people participated in here. And right now there are already several dozens, in fact, even not only repeating the experiment, but it was found in a different materials. What was really observed in here, extra current along the magnetic field. Usually when you put a conductor in the magnetic field, you have the Hall effect and your resistivity decreases. And that's what is shown, resistivity. But in this case, your resistivity drops, so you have an extra current. And there is an explanation, really, the curve is just a theoretical, you can describe this behavior. But coming back to heavy ion, closer to really the topic of this talk. So it's again, what is on the left, I just summarize what's happening. So you have your chirality imbalance due to the instantaneous phaleron, you put in the magnetic field, you have anomalous transport or charge separation. And so what's happening, it does depend on imbalance, really. Do you have more positive, more right-handed quarks or left-handed quarks? This current is up and down or perpendicular to along the magnetic field. And so, but anyway, so what you should look for, that the same charged particles flying, say, the same direction. So if it was positive, and negative particles would be flying in opposite direction. And that's the only thing which we know at that time. And so what I did, I just proposed this correlated to look at two particle correlations relative to the reaction plane, which now is commonly called a gamma correlator. And so what it does is just look if positive particles fly to the same directions. It can be rewritten like this, and that's where your contribution from CME is coming to. It also, once constructed this way, it also suppresses greatly other correlations not related to the reaction plane, because what it does is basically looks for a difference between correlations projected onto the plane and perpendicular to the plane. And so you have in-plane and out background, which is greatly cancels. And if you know that if there is something different in plane and out of plane, it must be related to elliptic flow, which usually characterized by this coefficient V2. And you can show that the only background which might exist for such correlator besides the CME contribution would be proportional to elliptic flow, and that's very important. It was realized very fast, and just in a weeks, so probably 3 weeks after the idea appeared in STAR, it was discussed, and the conclusion was that qualitatively the results go along with the expectations, but we don't know about the background, and not much real quantitative prediction from theory. And it's still almost true today also. We know much better. It was in 2004, but it took several years before the first result was shown in public. That happened in India, in Jaipur, in a poster. At that time, only in the poster, I was giving a talk on elliptic flow, just plenary talk, not on this subject, but also had a poster. And then later, in already next court method, STAR official presented these results, and we published some papers. And so this is just from the first papers of STAR, and so first results. And so what was done, we did observe that indeed same charged particles fly together. There is some separation, and so what is shown here is the same charge results and opposite charge result. There is a difference between them, which we could not explain by any model, although because we knew that the background, I mean, from the very beginning should be there, we checked many things and found that all models predicted maximum about 1/3 of the signal. And that's how it was reported. It was not reported as a discovery, it was reported just that no event generator could explain the stuff. And so we have just to investigate it more. What kind of background? So just a little bit more in detail for background, because it might be important to understand the results, which I'll discuss later. And so there are two types of background. This one, which is not related to, just related more to the technical measurement, and it's not that important for the data I will discuss today. Also, it is very important, for example, and basically invalidates all measurement, what is done up to now in small collisions like CMS results and even STAR results. But the background which is more relevant to us is this is due to the physics, and that's what I discussed, the difference between in and out, and so it would be proportional to elliptic flow present in the system. Where it's coming from? It's coming from collimation of any correlated pairs due to the elliptic flow, or difference in collimation due to the elliptic flow, collimation happening due to the radial flow. For example, if you produce lumescence over here, it's boosted by elliptic flow strongly in plane, and so the two pions, which are product of the decay, would be correlated, would be closer to each other in azimuthal space than if it would be produced over here and boosted out of plane. So there is this difference. This difference contributes to this correlated, because that's what we are looking for, correlations projected on this plane minus the correlation projected on that plane. And so that's the main background. As I mentioned, which is still true today, there is no any single event generator which would explain the signal. On the other hand, some mechanism which could produce a very strong signal was proposed. It was by Scott Pratt. It goes under the name of local charge conservation. And so local charge conservation is just not only some resonance, but whatever you have, you produce a cluster of particles. For example, the gluon is converted to quark antiquark, and so the charges are correlated at the same place, it's exactly the same mechanism of the background. This is the only known mechanism for the background. And it could create. And so if you run something like blast wave, put some parameters, in principle, you could get the signal or background which would explain the entire measurement. And that's, so you have to deal with that. And as was already seen in some previous slides, also I didn't discuss in details, just very first time we showed it in public, the results, we started to think and propose a program how to disentangle the background from the signal. And this is one of them, going with the isobars. That's probably, I could just skip the slide. And there are many, for over the years, there are many ideas proposed for those measurements. And for disentangle, some of them are realized, some still to come probably. But everything is based on the idea that your signal, CME signal depends on the magnetic field, and the background depends on isotropic flow. You have to play to vary one of them in order to get to disentangle. And the goal of the program is just to measure the fraction of contribution from the CME to this measurement which is done in the experiment, which I say only the event generator can explain 1/3 of it. But we want to understand how much real CME is coming. And initially, from the very beginning, even in 2009 or whatever, I said that we, in principle, should be able to go to 10% of this difference. Then it changed to 5%, and we will see that at least for isobars, we can do even better than that. And so there are many, some of those like isobars, and I will just mention. And before going to isobars, one thing which I want, this is the only not star results, what I want to show or discuss today, unless I get a question. And this is measurement from Alice using event shape engineering. And I think that it is most reliable measurement at this time or before this isobar, or again for larger systems. And so what was done in here, that by some special selections of the events, you can, even with the same centrality, for example, color here means centrality, for the same centrality, you can split this event sample in several, which would differ by elliptic flow, which means that you vary your background, keeping the signal more or less the same, because the magnetic field is mostly determined by spectators, which is the same at the same centrality. And so you can play on it, and that's the result for this, what I mentioned, the fraction of from CME in the measurement of this gamma correlator. You can see that the results are large. It can be consistent, so uncertainty is also large. And that's, again, as I said, it's most probably reliable and accurate measurement. Then I come to this isobars now. And the first idea, at least in my talks, I found that it was in 2008 when I mention it here. Sometimes I see the reference to that paper, but the idea is obviously simple. What isobars are is a nucleus of the similar shape. That's okay. I would say the same size for now, but different charge. And so if there's the same charge, you would expect that the background is more or less the same. We will discuss more details about more or less. But the magnetic field varies. And so the difference magnetic field enters, if you look for the difference in your signal in one isobar species and another, say ruthenium and zirconium. And this factor is about 0.2, just 10% of the charge squared. And then if you want just to go to accuracy, for example, for FCME, suppose you want to go to 10%, then it just means 10% by 0.2. It just means that in this ratio, you have to go or to measure this double ratio with the accuracy of, again, 2%, which is reflected and more estimates were done in this paper. And in here, it was what is drawn, which is taken from beam user request from star. So if the FCME is 15%, or it's written for 14%, then you would be able, taking this about billion events, 5 sigma measurement. And so it's sigma expected in this measurement is about 3%. The idea about isobar is clear. Which isobar to use wasn't clear. Also, I mentioned only this ruthenium and zirconium because it was run before in GSI in Germany, which I knew, and some interesting results were there. But there are several of them. And in STAR, in around 2016, quite large group of people, about 10 people, probably I would say led by Paul Sorensen, but there are many people contributed. I started to discuss which isobars would be useful to use. We came up with about 4 different isobars. 2 pairs probably the best, as I indicated over here. And frankly, I don't remember. So there are many things really was discussed. So it's we have to have large relative charge difference. They should be similar in shape. They should be available, which also related to price and possibility to accelerate. Also, RHIC is such that it could accelerate almost anything, including non-stable isotopes, really. And I found that in my mail that those would be expensive. Also, it's not clear why. Just after 5 years, I don't remember. I believe people from accelerators, they didn't like something about that. And so initially it was run with those. And so it was recommended to STAR that it would be run by the by PAC, the Physics Advisory Committee, that we should have a blind analysis for that. And that blind analysis was indeed, so a special committee and a lot of work was done in here. And so we started when I published a paper on how to organize such blind analysis. And there are several steps of it. From my personal point of view, the only useful or restrictive feature for all those stuff was that the codes and analysis nodes were frozen before the data, any data came. So you have to identify exactly what you would measure. You provide the code. All other stuff was not much really relevant. Also, it took a lot of work. Anyway, so it was also important just to have a systematic error under control, that your data collections was very uniform. And so we just alternate isobar species. There was a special, even again, program how to do it, which was reported by accelerator people and many other, so match luminosities. We also wanted to keep luminosity safe. And you remember I mentioned that in order to get say, FCME 10%, we need to have like a 2% accuracy. Our goal was about 0.5%, and we really reached it's even better, as it will be just seen. And how it was organized from an analyzer point of view. So we had 5 different groups. There was substantial overlap of some analysis between those groups, but in principle, all groups did its own QA. At the end, you even didn't run your own code. Somebody else from another group was running this code for you. That's quite interesting experience. And just for start, people and other people know really who was involved. And those couple slides I take from Jimmy Dunlap, who is the head of physics department at BNL, but also a star member. And for important for in here, yeah, he gave a seminar at BNL because one of the reasons, not because, he was a chair of GPC, or for at least people, IRC, for that paper. There is some acknowledgement here. I only wanted to mention that really Oak Ridge provided ruthenium. It was special run for them, and RHIC in Japan provided critical technology for zirconium. And so those are the results. I started the results. I have at least 20 minutes, I believe. So first, what was observed, so we do have some difference in elliptic flow. This is not related directly for CME, but it just means that background could be slightly different. And this is the ratio. This is just V to 2. You have several estimates of elliptic flow from different approaches using event plane, two-particle correlations, different delta eta gaps and other stuff. You can go into details. And the ratio between 2 is quite stable. And also the multiplicity production in 2 different nuclei is also slightly different. And you do have more charged particle produced in ruthenium. And so this is the ratio, about few percent. And it's not important what is the physics, it's also the physics is in partial, it was related to the larger charge of ruthenium. And so you bring this charge to the mid rapidity where the measurement is done, and that explains this difference that was partial. But what was measured, and that's important again, in overlap between all the group, that we measured this delta gamma over V2. And so even if some small difference in V2 was present, in this ratio, it would cancel out. And this ratio would be exactly the same for 2 isobar species, or the ratio would be equal to 1 if everything is 100% background, because we just normalize to V2. And so the difference or excess would be related to CME contribution. And this is the equations which I already discussed more. There are some technical also advantages of using double ratio. You don't need reaction plane resolution, for example, in those measurements. And there is difference, what is shown here from different groups. You see that we are quite consistent. Also, there are some small differences. And so this is the result for the full event, and this is the results for the sub-event. When you measure your delta gamma in one of the sub-event, this is my pseudo rapidity, and your determined reaction plane in another sub-event. And this also has advantages that you suppress non-flow. Also, in general, it's not that dangerous here. You suppress non-flow, but you also measure in some region where the signal is large. Okay, but that's what we measured. Again, you can see already from here, it's below unity, and what you expected, unity or larger. Also, it was immediately realized that it is related to multiplicity. But neither of the analysis nodes from all 5 groups contained this possibility. And so that's why the results were presented as was written in the analysis node. I'll come more to that. There are some other results, which, as I said, were attempted by different groups, but if this is kind of a standard candle, all groups were did. This result was done only, for example, one group. And so what is here, it just compares this ratio for the second harmonic. This is the definition, the standard gamma. But you can also change the harmonics in your measurement. And so if you change the harmonics, you wouldn't expect CME contribution. I could explain if there would be questions. Anyway, so you would not expect, but you would still expect some background. You cannot compare separately, say, take this one and compare with that, which sometimes is done, because the coefficient can be different between your background and in this ratio. But this double ratio, which is shown, you can do it, and there is definitely, should be sensitive to CME, because in this one, you do have CME contribution, in this one you don't. Both of them normalize such that if there is only background, it should be unity. And so you have to compare two numbers. That was done within the error bars, which is a few percent here. There was no any difference observed. There were another couple more differential measurements. And in here is done as a function of the difference in pseudo-rapidities of two particles. And you can see that it decreases if there is signal, or even background decreases. And so that's also explained if you're doing sub-event in smaller delta at the window, your signal might be better. You don't bring up more noise with higher particles, but you lose statistics. And as I mentioned, there is no difference was observed again between two isobar species. What is shown here is a function of invariant mass, excuse me, but as again, there is no any enhancement. One more measurement, which I want just to explain, was also done with isobar, which was by two groups, and that's related to somewhat different approach, which can be used for each isobar species separately. And so what it is on some effect related how the flow is developed. And so you know that there are some fluctuations in the shape of the initial geometry. And due to those fluctuations, your flow or elliptic flow, that's what is important for us, is developed along so-called participant plane, which fluctuates from event by event. But what is important, it does not coincide with the reaction plane. And so the idea was just to use this difference, because your reaction plane, or I would call it just spectator plane measured, which is closer to reaction plane, would be strongly correlated with magnetic field, while your background is strongly correlated with another direction, with flow. And it was known that it is different. It was measured by star before, but this is a slide from Alice. Both of them are just qualitatively the same. So this difference between those planes leads to the difference in V2 by about from 10 to 20%. And so similar to the difference in the chart. And you can play on it. That is discussed in more details. Again, instead of two isobars, what you do, you construct the same or similar double ratio, but using spectator plane and participant plane. Again, your particular results which are shown here is coming from the group 4, which is just Takafumi Need and myself. All plots are really, from our group. And so we used ZDC in also some specific manner. And so that's again the expectations in here. And so you can extract this FCME, what we see. So for actinium and for zirconium, this is for double ratio, and this is for FCME. Here you're not affected by difference in multiplicity or anything else, to do totally separately, but you conclude that signal is again consistent probably with 0, with a sigma here around 10%, a little bit more than 10%. It's because your resolution from spectators is not as good. This is a summary plot, and so, there are two summary plots in these papers, and because we felt that we need something to say about this difference in multiplicity and its effect. Also, it was not kind of in our predefined observables, and so we agreed, because it should be very short, and in fact it is only 2 paragraphs, I believe. But the summary plot is, there are 2 summary plots, and one plot is before this post-blinding. In the post-blinding version, there is only 1 point, really 2 points, but I will talk about this point added, and this is the ratio of multiplicities. And so the reason for that is, once we saw that multiplicities difference is significant, it was immediately clear that because any two particle correlations due to small clusters is the background or the signal, they would scale inversely with the multiplicity. Say you have rho meson, you pick up 1 pion, and the probability to pick up another charged particle from the same resonance would be inversely proportional to the multiplicity. So this multiplicity must be included. And so if it would redefine your baseline. It's not unity anymore, but the ratio of the source multiplicities. And if you include this multiplicity, you can see that the signal says those are results from sub-event measurement, and there are some results from the full event. And this is a sub-event. They are kind of touching, so which would be consistent with 0. But there is no any puzzle in terms of why it is as it is. And so going a little bit more details, so that was the only, we wanted to keep this post-blinded section as very short, and so this only indicated. But in principle, in the data itself, we did publish, and I already showed the multiplicity, for example, this plot, the multiplicity ratio. And we did show the results, again, for centrality dependence of delta gamma. Both of those shots are shown in like later slides. And in principle, you can look also if this idea that it should be scaled with multiplicity holds as a function of centrality, because it is also changing with centrality. And so what I did for this presentation, because I don't want to create any new data or plots, so for this presentation, I just cut out this part. I rescale it just to match it with other plot. I flipped it vertically and overlay. And so this is my inverse of that part. And you indeed see, and I think it is important to realize that even centrality is, or ratio variation with centrality, it's non-monotonical, is due to some, it's related to centrality determination. But anyway, so it's the idea that it scales with multiplicity holds quite well. And I mentioned that with the achieved accuracy in double ratio, we should go to the accuracy in fraction of the CME of a few percent. And just to show it again, it's not an official plot, don't use it, but it comes from comparing of this dashed line with one of the data here, named group 4. And indeed, you see that that kind of FCME you would expect, but I have some more wording later. If you would do, if you average from 20 to 50 centralities, that's what we initially wanted, and all these summary plots are for this one, you can go to accuracy about 2% or 3%, a little bit more than 2%. But we didn't go, it was not announced, I mean, it was not, say, predefined, but there is also another reason, because right now it's clear that the signal is very close to 0, and in fact, to make this scaling, you have to think a little bit more, and to establish this exact limits, you need to understand the systematics. For example, say if non-flow is different between those, because we can go to sub% level accuracy in the double ratio, real almost per mil difference. And so if just non-flow contribution here is different by, say, a few percent, and the contribution itself is about, say, 10%, it still would contribute. And that is what is happening right now. So in STAR, we want to understand all the systematics. It can be done, nothing as a showstopper real here, to estimate. And then we would report, the STAR will report is the upper limits of some signal. We will see what is done. And by the way, some difference, that's what I'm talking about, the sub% level, it can be seen already in this plot. Namely, if you compare your sub-event and full event, you see there is some small difference. And this difference is coming just from the effect which I mentioned here and which we want to understand better, I mean, with better precision. Why it's different? Because, for example, non-flow contribution is smaller in sub-event measurements than in full event. But if the ratio of non-flow to flow was the same in two species, you wouldn't see the difference. So it's a little bit more complicated, but it can be done. And so as a last plot from the data, which I already mentioned, so there is another paper submitted from STAR, and that measurement is on gold, and it's related to this method which I mentioned about measuring relative to spectator and participant planes, which for isobars separately I reported over here. Remember, this is just a measurement. It can be done for isobars, but it can be also done, and in fact, with slightly better accuracy for gold. And that is just a measurement from this paper. Again, if I look for mid-central collisions, if I look for sub-events, again, there is some difference between sub-events and full event. You can see that also consistent. Also, it's very close to 0, but it's also consistent with some small signal. And so we could ask ourselves if this is consistent with what we see in isobars, because isobars definitely exclude, say, 10%, so even 5% probably. So if there is something, it could be smaller. And that's the last plot, the last my slide. So what I want to say, yeah, that's already announced, that we can measure. So we did measurement. It's very important. It's a beautiful data, in fact, and many analyses are already in processes for this data, as not related to CME, and some of related to CME. But if you want just to compare with the gold, I would say that there is no contradictions, because it also was somewhat later realized that the signal in smaller system expected to be smaller than in larger system is due to the, again, magnetic field, and more exactly to the lifetime of the magnetic field. But there are some other processes which also, but whatever you could say, whatever, there are several, say analysis and even papers published. Some of them predict that in smaller system, like isobars, you would have the signal about 3 times smaller. Some of them, which I would just refer, at least people would know as this plot from Alex Dobrin groups, which try to compare the signal between lead and xenon. And that is almost an order of magnitude. So there is no contradictions, but nevertheless, that's the status of what everything we have. And I will stop here just to have 5 minutes for questions. So thank you.
Okay, thanks, Sergei, very much for this nice talk. So now we are open for the questions. So I already see one hand raised.
Okay, just sound.
So
Vedanta,
can you?
Yeah, I have 2 questions. One on slide 27, where we have this ratio for the signal divided by the V3 ratio as a background. What we see, what we see in the measurement, these ratios are of similar value. So ideally, the right-hand side ratio should have been 1. It is not. So why should I consider that as a background to the signal? The gamma 1, 2, 3 by V3, ruthenium by zirconium.
So what? Both of those ratios, this one and this ratio, in order to compare with one, as I already mentioned, I have to multiply by multiplicity of, say, zirconium divided by multiplicity of ruthenium, both of them. Then you would expect this ratio to be 1. And it will be 1, as we did see, because the multiplicity ratio is just approximately over here.
I see.
But what I wanted to emphasize that even if you don't know about this stuff, you would expect that this ratio, if there is a CME, should be larger than that. And we don't see.
I see. Okay, one other last question from my side. We have gone to a precision of less than 1% in our observable. And what you showed is CME fraction is less than 5% if we take that plot. So how more can we go precise? Because it's already like 0.4, I think, percent is the precision.
Yeah, as I mentioned, I expected initially, say 10 years ago, that we can go to 10%, but probably unlikely, better better than that. Now we went to at least a few percent, so 2-3%. I don't know how it can be done better. In principle, and the other problem is that RHIC will run only a few years. It's unlike the isobars. Also, in principle, if it would run of heavy isobars, where we do expect signal better measurable, yeah, we could do something. But other than that, we can explore some other observables, including identified particle and other things. But I'm not very optimistic, right, that we can go better.
I see. Yes, Sergei, so thank you very much for this nice
Yeah.
talk. That's all from my side.
You're welcome.
Okay, so next question by Swasisda. Swasisda, can you please ask?
But yeah, so, thanks, Sergei, for this wonderful talk. Now, I have one question which is related to this precision thing. The way I understood at the beginning, you said that for a signal of about 10%, you needed something like 0.5% or something. And when you got 0.4%, you thought that, yes, we have enough precision. Now that the signal level itself is 2%, means if I take your final slide, some of them, do you think that the precision is enough? This is question number one. And question number two is that all that we discussed earlier with the correlation results, where there was a strong charge separation, and now they are all, means where you said that 1/3 of them could be explained with the models, 2/3 are not explained. So they were all background, and they started changing with beam energy scan. So any comment on that, that lower energy something might happen or not happen? Okay, thank you.
So as yeah, for beam energy scan, I probably didn't understand, but let me just first one by one, so we can you can ask other question as well. What I was showing in this plot, that's where indeed, so this is the difference which is expected from the difference in magnetic field, and I discussed, so if this FCME, for example, 10%, that only this ratio should be measured by 10% by 0.2 with the accuracy at least of, I say, 2%. But we measure it better, and it's related really to what STAR promised to DAE and to community in some sense. When STAR asked for running isobar collisions, they said that if the signal is such, we would be able to measure with this precision. And it is important, and that's why everybody emphasizes, including me, that we did reach what we promised, but the signal is not what it could be, so it is much smaller. So that's just explaining this part. And then about this, you mentioned, I hope that's clear.
Yeah.
So we did measurement what we promised in some sense, but we don't see the signal. About this 1/3 of the event generator, and I mentioned that indeed all existing event generator cannot explain the measurement. It's probably sometimes it's still slightly higher than 1/3, but it's always less than 1/2. And so you have to put something extra. And so there are some models where you put an hydra, which is not an event generator. And then you put by hand some stuff. You enhance your, say, cluster contribution, which can explain almost all the data. And so what I was hinting that we still lack a good or an event generator which could describe our physics, which we definitely need for many things. Otherwise, we don't understand. We are saying that it is background, we see that it is background, and no event generator, say MPT, does not describe it. And so how much we can really rely on those generators and other questions. That's about, at least that's what I wanted to say about this one. So.
No, I understand. Thank you very much. Now, can I just, Siddharth, just one second? If I remember correctly, is that when the top energy correlation measurements were done, and then the results that we talk about, and then as we go in the beam energy scan, this values started going down and down, and it almost vanished. And it was thought to be kind of vanishing of the signal which was seen at top energy. So now that nothing is seen even at top energy, do you see any argument on this direction or need of, for example, even isobar at lower energy?
I probably don't have the slow energies. Yeah. Your recollections about low energies is not totally correct. At least the conclusion, also the error bars are large, but the conclusion was that the lowest energy, the signal is kind of disappears, which in principle would be consistent with the chiral symmetry breaking at very low energy. But it's not zero and say beam energy scan 60 or 30 G. And so a more precise measurement would be indeed very interesting, and they're going, in fact, for beam energy scan with highest statistic beam energy scan 2 for the star, what I'm saying. Why it wasn't done before, it's because the resolution you need the, I mentioned, to measure the spectator plane. This is the most precise probably measurement, the spectator and participant. You need the first order reaction plane from spectators. And the DC acceptance is bad for low energy. But with this event plane detector, EPD installed, we can do it. And that's how people analyze right now. So they use the first order event plane, EPD at low energy, pick up some protons. And so you can do a similar measurement at low energies. So what was interesting, also not fully realized, that now people pay more attention on not on the absolute value of the signal, but how it can scale. And that's what with Alex Dobrin we also just investigate, how it scales with energy, with system size and other things, relatively similar to what we discussed for background. And because the magnetic field time dependence, say, I can draw. So if you have a time, and here's just the magnetic field. So for higher energy, it's something like that. So you have a peak, and then for lower energy, it started with lower value but lives longer. And this is another hint that in principle, the signal can be larger in beam energy scans than even at top RHIC energy. And so it's, I don't know, fortunately or unfortunately, but it's not the end of the story. And I believe more measurement will be done, including the beam energy scan.
Thank you, Sergei. Thanks a lot.
Okay.
So, yeah, just on this point, so Sergei, we have these ions, ruthenium source and zirconium. Why can't we propose a beam energy scan for isobars?
Yeah, you kind of remind, it was in air, it was discussed, and probably we could get even some more help from, to push it from theories, I think we can propose. Another thing is, again, to consider now, because it's already clear that the small system doesn't help, we could again revisit this stuff and run, for example, with those isotopes. But it is important, yeah. I would think it should be discussed. It was discussed briefly by several people. I think we shouldn't. We should
Yeah,
push
we
for
should.
it. I would be for it.
Yeah.
Yeah. Especially that it's clear that this isobar sample which we have right now, right? It is because it's also the systematic is very low. Our systematic everywhere is below the statistical, and it's used, for study even the shapes of nuclei and many other things. In this sense, running isobars appear to be very useful. And we can probably collect from different groups what can be done.
Yeah, thank you.
Okay, thank you.
So I do not see any more hands. Am I missing someone? If anyone else wants to ask. Looks like not, then probably I think we should conclude then. Thanks, Sergei, again for your time.
Okay, thank you for invitation again.
Yeah, and thanks
Bye-bye.
to everyone else for
Thanks,
joining.
Sergei. Thanks, Ben. Everybody, bye-bye.
Yes. So I stop sharing. Bye-bye.
Bye.
Thanks a lot.